Welcome back, fellow electrical engineers and grid professionals, to another explainer. Today, we are tackling a critical, high-stakes topic that is fundamentally reshaping how we plan and protect our power systems. As our infrastructure rapidly modernizes, we're facing this escalating threat from high-frequency transients. And let's be clear, these aren't your typical grid fluctuations. We're talking about incredibly rapid, severe stresses that can push our equipment to the absolute breaking point. I am so thrilled to guide you through this complex landscape today, to break down the science and give you a clear, structured look at exactly how we analyze and defend against these extreme events.
To set the stage, I want you to think about a fundamental question for a second. How do we actually protect the modern power grid from invisible microsecond electrical shockwaves? Because, honestly, that is exactly what transient overvoltages are. They are violent, invisible shockwaves that can utterly destroy critical infrastructure, wreck equipment insulation, and cause catastrophic system failures before a standard monitoring system even registers a blip.
Okay, let's dive into this. Here is our roadmap for today's explainer. 1. The threat of transients. 2. Slow front overvoltages. 3. Fast and very fast overvoltages. 4. Analyzing with EMT modeling. And 5. Mitigation with surge arresters.
Starting off with Section 1, the threat of transients, the grid's invisible stressors. It's no secret that as our grid shifts toward a decarbonized landscape, one that's heavily reliant on inverter-based resources like solar and wind, we're facing entirely new rapid stresses. Now, as engineering professionals, you are already deeply familiar with steady-state operations. Under normal conditions, our components hum along comfortably within about 10% of their nominal voltage value, right at that nominal power frequency. But a transient overvoltage, that is a completely different beast. These are extremely short-duration events. They're highly oscillatory, usually heavily damped, and they subject circuit components to just immense stress. In fact, frequent overvoltages with smaller amplitudes but a really steep rate of rise can be just as hazardous to your equipment insulation as a single overvoltage with a massive peak amplitude. Now, what's really interesting about this slide is how we visually classify these standard voltage shapes based on IEC guidelines. You can clearly see the distinct waveforms that differentiate temporary overvoltages, which might last for seconds or minutes, from the sharp, sudden drops and spikes of switching and lightning overvoltages. These standard voltage shapes are precisely what we use to design our withstand tests, basically ensuring our insulators and transformers can actually survive the real world.
Moving on to Section 2, slow front overvoltages, otherwise known as the switching surge.
By definition, a slow front overvoltage takes anywhere between 20 and 5,000 microseconds to reach its peak. It's characterized by high amplitude, it can be unidirectional or highly oscillatory, and it features a highly damped wavelength. Once it hits that peak, the tail duration resolves in fewer than 20 milliseconds. Now, I really want to emphasize this point. Despite being called a slow front, we are literally talking about an event that peaks in a fraction of a single millisecond. Slow is very relative here.
So where do these originate in our daily operations? The primary culprits are actually routine switching operations. Every time we energize a line, switch a capacitor bank, or clear a fault, we run the risk of generating an SFO. They can also be caused by direct lightning strikes to overhead line conductors. And because they happen so frequently during standard operations and testing, designing the air gap insulation for transmission line towers to withstand these SFOs is a routine but absolutely critical engineering task.
Let's move to Section 3 and see how this builds. Fast and very fast overvoltages, accelerating the timeline. A fast front overvoltage is a unidirectional transient with an exceptionally short duration. While SFOs are often tied to that routine switching we just talked about, FFOs are most frequently the result of severe external events, specifically massive lightning strikes or operations at a disconnector switch. The sheer danger here is the absolute speed of the energy transfer. It can cause immediate, severe, and often completely irreversible damage to your electrical equipment, like insulators and transformers. To put that speed into perspective for a second, just look at this number: 3 microseconds. That's it. A fast front overvoltage typically completes its entire total duration in fewer than 3 microseconds. By the time a conventional mechanical relay even begins to react to a fault, an FFO has already peaked, dealt its thermal and dielectric damage to your transformer winding, and completely dissipated. And pushing into the absolute fastest transients, we have the very fast front overvoltage.
Now, this is a highly specialized threat. VFFOs occur almost exclusively in gas-insulated switchgear, or GIS. They happen because of the incredibly rapid dielectric breakdown of the insulating SF6 gas during a switching event or a fault. We aren't even measuring in microseconds anymore. VFFOs operate on the nanosecond scale, pushing frequencies up to 50 megahertz.
And this brilliantly illustrates the complete spectrum of the threats we've just discussed. There is an inverse relationship at play here. As the event duration shrinks from thousands of microseconds down to mere nanoseconds, the rate of rise sharpens, and the specialized stress on the grid's insulation materials becomes increasingly extreme. Understanding the breakdown on this table is absolutely fundamental for proper insulation coordination.
Which brings us to Section 4, Analyzing with EMT Modeling, Seeing the Unseen.
Because these events happen so fast, traditional steady-state or phasor domain simulations, the tools the industry has relied on for decades, are entirely blind to these rapid electrical events. We literally need a way to see the unseen. This is why electromagnetic transients, or EMT modeling, is strictly required today. EMT simulations utilize ultra-small microsecond-level time steps to catch these fleeting events. But more importantly, EMT allows us to model frequency-dependent effects and the nonlinear characteristics of equipment, like core magnetic saturation and transformers. It is also the only way to accurately evaluate transient recovery voltage, or TRV, which is that severe voltage stress that appears across the contacts of a circuit breaker the exact instant it tries to clear a fault.
Executing an EMT study isn't just plugging in numbers. It is a rigorous, highly specialized procedure. First, you must determine the exact frequency range of the transient you're investigating, whether it's an SFO or a VFFO. Second, you have to build high-fidelity models of the physical components. This means intentionally modeling stray capacitances, mutual inductances, and structural core characteristics that you would normally just ignore in a basic load flow study. Finally, you execute the simulation using those microsecond to nanosecond time steps to capture the true rate of rise and amplitude of the shockwave. And finally, Section 5, Mitigation with Surge Arresters, the hardware defense.
So the crucial point is, once we've successfully modeled and identified a transient threat using our digital tools, how do we build a physical shield in the real world? How do we actually redirect that violent energy away from our sensitive equipment? Well, zinc oxide, or ZNO, surge arresters are the industry standard. They operate on the principle of nonlinear impedance clamping. Under normal steady-state voltage, they basically just act like an insulator. But the moment a high-voltage transient hits, their impedance drops dramatically, allowing them to instantly conduct the surge to ground, safely absorbing that transient energy before it can tear through a transformer winding. It's like a pressure relief valve for the grid. But beyond surge arresters, engineers have a pretty robust toolkit for mitigation. We use surge capacitors placed directly at breaker terminals to lower the rate of rise of transient recovery voltages. We deploy controlled switching devices to perfectly time contact separation with the point-on-wave to minimize arcing. And we utilize pre-insertion resistors to add temporary series resistance to a circuit, which effectively dampens those harsh switching surges that cause slow front overvoltages in the first place. To tie this all together and summarize the necessity of everything we've covered today, I want to read you this powerful quote drawn directly from the research material. The detailed investigation of transient recovery voltage and transient overvoltage through EMT modeling is no longer optional. It is the only viable method for identifying and mitigating rapid, nonlinear stresses. In a grid that is increasingly dominated by renewables and fast-switching electronics, mastering these tools isn't just a recommendation anymore. It's an absolute mandate. Which leaves us with this final, critical thought. As our power grid becomes entirely digital, decentralized, and inverter-based, the invisible stressors are only getting faster and more complex. So is your transient analysis fast enough to catch the next shockwave? It's a question every single grid operator and planning engineer must be prepared to answer. Thank you so much for joining me for this explainer. Keep your models accurate, and I'll see you next time.